Much like people do, inhaling and exhaling, land surfaces also do the same thing. They inhale carbon dioxide. They also release carbon dioxide through respiration. And we're able to use these instruments to really monitor that breathing of the terrestrial biosphere at anywhere between every half an hour to the entire growing season. One of the challenges we faced when attempting to study the largest tundra fire over the past 50 years was how to first get our instruments here, and secondly, how to power our instruments. We are currently about 40 to 50 kilometers away from the nearest road and 40 kilometers away from Toolik Field Station. We faced a dilemma. How do we power instruments in such a remote part of the world? And we got over this challenge by utilizing solar panels. So we have two solar panels here that are connected to a solar charger. And that charge controller is connected to two 100 amp hour batteries. And these solar panels allow us to maintain our equipment and keep it running throughout the whole growing season and partly into the winter season before it's too dark to recharge our batteries. We have a bunch of instruments out there that are measuring things like wind speed, sunlight, temperature, precipitation, CO2 concentrations, and water vapor concentrations. Right now we're utilizing a technique called Eddy Ecovariance. And Eddy Ecovariance is a technique developed in the micrometeorological community, but more and more ecosystem ecologists are learning about this technique and using it to determine the overall breathing of the terrestrial biosphere. And what I mean by that is that photosynthesis bringing in carbon dioxide from the atmosphere and respiration from the microbes and fungi, sort of releasing that carbon back into the atmosphere. So those two processes are known as fluxes. So what I'm doing here is exchanging out the open path gas analyzers, because the one that we have currently out here needs to go back to the lab for calibration. It's an open path analyzer and it allows you to measure CO2 and water vapor in the air. And the way it does that is that there's a detector and an infrared light source in here that, because CO2 and water vapor absorb in the infrared, you can use that signal to detect how many molecules of those gases are in the air that flow through past these two sensors.
And what's the crazy little black bubble?
That is measuring radiation, sunlight basically. It's measuring both the direct rays of sunlight and the diffuse rays of sunlight. Diffuse light is basically if you have a cloudy day and no like direct sun, that's called diffuse radiation.
Got it. The Kip and Zonin?
That is measuring the components of sunlight. So it's measuring not only what's coming in from the sun, but what's being reflected from the land surface. And it's also measuring the infrared component of radiation. So as the soils and vegetation warm up, it's emitting long wave radiation. And we're monitoring that long wave radiation, and also the molecules in the atmosphere are emitting long wave radiation as well. So we're measuring both the upwelling and downwelling components. And what's really nice about this data is that we can get these fluxes at timescales from every half an hour to the entire growing season. So we can relate these fluxes to how much light is coming in, how warm it is outside, how much precipitation the ecosystem received. We can start relating those variables together and developing predictive models to sort of project what we think will happen to the carbon cycling in the tundra in the future.